Hello, welcome to Quantum Computation Explained. So you would have seen my previous set of videos, Quantum Computation Simplified. So there I was trying to remove the fear of quantum computation coming from quantum mechanics, and then trying to give a very high level explanation about quantum computing. Whereas in this video I'll try to go slightly deeper into the subject so that you will start using and practicing and come out with great algorithms. So apart from that, we will also see what is superdense coding and teleportation in this video. So this is made for whom? So this is made for those who are aware of quantum computing. So like as I told you, uh, if you have seen my previous video, it is good. If you have not seen, you please either go through that video or another videos on the subject, or you can study some textbooks for better understanding of this video. Okay. And then those who want to learn quantum with that kind of awareness, those who want to learn computer programming or building an algorithm for quantum computer. But certainly we are not going to talk about quantum mechanics. For two reasons I don't want to talk. Only first reason, I myself don't know about quantum mechanics. The second reason is you really don't have to know about quantum mechanics to be a good programmer of quantum computing. So we'll go on to have a recap on qubit and qubit manipulation. So this slide is very important. I'm going to spend more time on this, and please try to catch every bit of it. So what is qubit? Qubit is quantum mechanical equivalent of a classical bit. So in a normal computer, we know there are many, we have classical bits, right? 8-bit machine, 16-bit, 32, like that. So in quantum computer, we'll have quantum bit or qubit. So how we make, so qubits can be made from photon, electron, atom, superconducting circuit. So again, we will not go into the detail because this needs a lot of expertise from quantum mechanics, and physicists are doing great work and they are trying to give us the best qubits. Our job is to see how to manipulate those qubits in order to solve our problem. And typically, which will become eligible for qubit is wherever there are, there is a chance for uncertainty, like photon, no? You can have vertical polarization or horizontal polarization or in between. So that is where, it creates some confusion, but at the same time, that really gives the advantage of uh, advantage for qubit over classical bit. So before we see how to manipulate, let's understand mathematically how do we represent, because that is very important. So if you take a classical bit, it can take the state of 0 or 1, any one state. So you don't need a big representation. So afterwards you apply some gate, then you manipulate those bits to get the required solution. Whereas in qubit, apart from 0 and 1, what is represented here, it can take any intermediate position, a combination of 0 and 1. So that is why you cannot just put like a discrete expression like this. You need something more than that. So people use something called the block sphere, what is given here, and then the state is represented not with plain 0, you have ket 0 and ket 1. And I think if you are not familiar with that, please see my previous videos where we have seen Dirac notation having bra and then ket way of representing the states of a qubit. Okay, and this also represents a vector. When you say ket 0, it is a vector of this point. Similarly, one is a vector from coming from origin. And in between, what happens? Suppose you say there is a qubit that's somewhere here. Then how do we call them? Actually, here it is simple, ket 0, and here it is ket 1. in between we can call it like this, okay, cos theta by 2 ket 0 plus e to the power of I pi sin theta by 2 ket 1. So what it shows, I mean, it shows two things. One, it is a combination of 0 and 1, and also there is a coefficient associated with 0, 1. They determine the magnitude of 0 content. So what is the use of the magnitude of that 0 content is when you make a measurement. So whenever you make a measurement on a qubit, it will reduce it to classical bit. So it will take either 0 or 1. It no more can hold zero, I mean a combination of 0 and 1. So at that time the magnitude plays a role in getting the probability of getting a 0 or 1. So higher this number, higher probability of getting 0. So as you go up close to that, you have a higher probability of getting 0, and at this point of, I mean at this point in the sphere, 100% you will get 0. But as you move down, slowly the 1% will keep on. I mean, meaning if you make a measurement 100 times, so here 50% of the time you get the 0 value, 50% of the time you get 1 value. And as you go down, the number of times you get 1 will keep on increasing. And here 100% of time you will get 1. The probability of getting 1 is 1. And at the equator region, and particularly facing this direction on the x-axis, it is written as 0, 1, I mean ket 0 plus ket 1 by square root of 2. So why this square root of 2 coming? Again, if you don't remember, you have to see my previous video. And then the state just opposite to this will be ket 0 minus ket 1 by square root of 2. And here on the y-axis, which is actually an imaginary axis, I mean for representing a complex number, so the whole thing is in a complex plane. So you have I times ket 1, okay, so ket 0 plus I times ket 1 by square root of 2. So that is, I mean, this is how it is represented. And some people they represent it in two-dimensional form, but the drawback is you cannot represent phase. So what is that? For example, if you take this latitude, so I mean you draw a circle like this, and anywhere on the circle the magnitude will be same, but they have an intermediate phase coming from this pi. So that cannot be represented in a two-dimensional form. That's why this is being widely used, and this is again, it's not the right thing to represent the state of a qubit. At least I know there are two issues, I mean two confusions. See, states 0 and 1 are orthogonal because bra 0 and ket 1 will give 0. You know that two vectors, when we do dot product, if the result is 0, they are perpendicular to each other. But in this case, we are saying they are 180 degrees out of, I mean, there is 180 degrees between the two. So, which means it's wrong. But for representation that you have infinite combinations of 0 and 1, we are making use of that. The second problem comes from the angle. So though we are saying it is theta, but we are while writing we are saying theta by 2. Again, there are different explanations. The one simplest one we can say here is, if I start from 0, I have to apply 180 degrees to go to 1. But if I apply pi, I won't get 1 here, right? So I need to apply pi by 2 then to get 1 here. Then only you will get 1. So that is another problem. Not problem, it's a confusion, okay? But still, don't worry. Once you start manipulating with the gates, you don't really look at that unless, I mean, except for visualization of the results, okay? So the conclusion is, qubit can take the state of both 0 and 1 simultaneously. So this is what is important, which means it can be in a superposition. I mean, position of 0 and 1. And that gives tremendous advantage of qubit over classical bit. Let's see how it is useful in quantum computer and how it gives power to quantum computer. So let's represent number 2, okay? The decimal number 2 and 6 using classical bits and qubits. So I'll make use of 3 bits, classical bits, because we need to represent 6. So when I have 3 classical bits to represent 2, what I'll do? I'll say it is 0, 1, 0 in binary form. and then for 6 it will become 110. So with 3 classical bits, I'll be able to represent either 2 or 6. Okay, one at a time. When you come to qubit, so if I want to represent 2, I will have to say 0, 1, 0. Right? North pole, south pole, north pole. And 6 will be south pole, north pole, 1, 1, 0. So you may ask, what is the difference between the two? The difference comes when we fiddle with this qubit. So instead of taking keeping it at 0, we will apply Hadamard gate. I think you remember Hadamard gate, which will bring the state from 0 to this state. Like this it brings. So now this has got two states in it. So what are they? It has got 50% 0 state, 50% 1 state, and they are all 100%. So they are all in 1 and 0. Now if I see the combined state of 3 qubits, I have to take tensor product, right? So if I take combined one, I'll have 0, 1, 0, 0, 1, 0, and I'll multiply 1, 1, 0, 1, 1, 0. So both are there simultaneously. So meaning I'm able to represent with the 3 qubits both 2 and 6 simultaneously. Okay, so 50% of the time it will behave like 2 and 50% of the time it will behave like 6. Now with one qubit bringing to superposition state, we are able to get some benefit. If I make the remaining 2 qubits also to superposition state, now what we can do? We'll be able to represent from 000 to 111 all the combination of decimal number 0 to 7. That 8 combinations are possible with 3 qubits. Suppose if we have n qubits on hand, we will be able to raise 2 to the power of n states possible. So 10 qubits, 2 to the power of 10 combinations. A number as large as 2 to the power of 10 can be represented simultaneously. Please remember the word simultaneously. So that is the biggest advantage of quantum computing. Okay. Shall you see what is the advantage with an application? Okay, so I'll be using a tool, an excellent tool to simulate quantum bits. So it has got other example circuits also, but straight away we'll get into the tool. Again, I will not explain each and every aspect of the tool that itself. It will take a video, and already there are videos on that. So, but we'll see the important ones what we are going to make use of. So we are always given 2 qubits which are all in 0 state. We can increase the qubit by adding more and more gates. We can go up to 16 qubits, I believe. And then these are all the gates. You can make use of them by pulling them to this line. And then these are all a kind of outputs we can say. So this will say what state it is in. So it is currently in off state, and off means 0, and this also is an off state, and this represents Bloch's pair. Okay, so the position of qubit on the Bloch's pair is given. This is the one which will be interested, because in a practical quantum computer finally we'll make measure the result, and then this gives what is the magnitude of getting 0 0. Okay, so with 2 qubits we can get, actually we can represent get 4 values, right? 0 0 1 0 1 1 means 0 1, but today we don't have any magnitude for that. So that is why we are going to apply Hadamard gate. We are going to excite them, and now we will be able to give superpositions to these 2 qubits. So now it has become 50% on, 50% off. Same thing for this qubit also. And the result is interesting thing, right? So you have all combinations possible. We are in real superposition state. So there is a chance if you make a measurement 25% of the time you will get 0 0, like that, 0 1 1 0 1 1. So now with 2 qubits I have 4 combinations, but I am interested to take out, I want to manipulate such a way I want to get 1 1 alone. Okay, this is something like Grover's algorithm. You remember, there is, if there is a huge database, unsorted database, you want to get one guy or one item from there, instead of checking every data available. So I want to go and straight away pick that. So that is possible. So let us see how that is done. So here I want to take 1 1. So for that I need to build an oracle. Oracle is nothing but a set of gates. To differentiate out of 4, I want to differentiate only 1. So what is that? So let me do an operation called Control Z. Okay. So now I'm able to differentiate. You can see here, right? These 3 are having phases 0, whereas this alone is having phase 180. So I'm able to mark that what I'm interested in. But if I make a measurement, typically in a quantum computer, after doing some manipulation, we'll go and make a measurement. But if I make a measurement, it doesn't give me anything. So what it gives always same, like 25% of time I will get 0 0, 25% 0 1, and 1 1, 25%. So the probability of getting 1 1 is 0.25 only. So that is not sufficient, right? I need to get higher probability for the number I am interested in. So for that only Grover has given diffuser operator. So let's do that. So for that some more set of gates we have to apply. Now after applying that, you can see some magic has happened. So all other states have disappeared. We have only 1 1. So any number of times, if I make 1000 measurement, 1 lakh measurement, always I'll get 1 1. Great. So this is possible because we have only 2 qubits. Suppose I have say a million qubits, so you won't get in one shot. So what at that time the probability or the magnitude slightly it will be higher than other data. So at that time what you have to do is you have to repeat this process slowly. It will increase the probability or the magnitude will go up. So how many times? Maximum number of times, I mean, it's limited to square root of n, where n is the size of your problem. Okay, so you don't have to go beyond I mean square root of n. So that was giving advantage, right? Instead of checking every n data, you can do only I mean square root of n times. But again, you really don't have to go to that far because before that itself you will see a good difference in terms of magnitude for the one what you are interested compared to other one. So what is happening is, I mean, in simple terms, with say 10 qubits, you can have 2 to the power of 10 combinations, and then you can do simultaneously some operation. So that is where a bit of, I mean, a sort of parallel computation is possible with quantum computer. So that is where you gain the big advantage. Okay, all right. What other applications you can think of? One possibly, yeah, you want to even for prime factors, people use this approach. I mean, basically you are looking for 2 numbers, right? So that number, if you can characterize with a set of gates, you'll be able to pick those 2 numbers. Or if you want to find a pattern in a matrix or in a picture, so you have to define the problem such that this alone, I mean, it will search, I mean, it does parallel computation and gives you the result what you are interested in. Okay. And I mean, you can do a lot of manipulation. For example, if I remove this gate, it gives you different one shape. Again, it changes the face. You can see nicely. I mean, like this, you can play with this. Now you see different combinations. Like that, you can do many things. Okay. I'll come back to normal thing. So we'll go back to the presentation. All right. So we have seen the advantage of superposition. Now we'll see another property of qubits. It's called entanglement. So what is entanglement? An entangled state is essentially a superposition of states of different qubits in such a way that they cannot be factored into a tensor product of individual states. It's a little complicated, so let me try to. So yeah, let me try to explain it with an example. Suppose we are given two qubits. So I mean they are in the combination of 0, 0 and 0, 1. Can you say whether they are entangled or not? Yes, we can do with this definition. If I'm able to represent them separate into two qubits, then they are not entangled. For example, 0, 0 and 0, 1 can be represented by two qubits separated with one qubit is in state 0, the other qubit is in a superposition state, a combination of 0 and 1. So as an example, if you take alpha is 1 and beta is 1, so it is in the equator region, right? So 50% chance of 0 and 50% of 1. So when I make a tensor product, I'll get 0, 0 and 0, 1. So which means I'm able to separate these two qubit states into two individual qubits. That means they are not entangled. But if we are given a pair like this 0, 0 and 1, 1, so whatever you do, you just can't separate them. So that's why they are called entangled. Okay, so what is the use of entangled pair? Actually, today we don't have much use for quantum computation. I mean, as you can see, most of the popular algorithms like Deutsch, Grover, Shor, I mean, they don't use entanglement. But they are used today for superdense coding or quantum teleportation. Basically, they are for quantum communication, quantum network. And there are some algorithms still they use. In fact, I think if you remember the solving linear equations, you would have noticed some of the qubits got entangled, okay? So, but still we haven't really come out with great applications using this entanglement. So before that, let's try to understand what is superdense coding and what is teleportation. Okay. So superdense coding is a quantum communication protocol to communicate several, please note the word, several classical bits of information by only transmitting a smaller number of qubits. That means if I want to send 100 bits of data, classical data, I need not send 100 bits. If I send 50 qubits, that is sufficient. Okay, so that is why it's packed information you are sending. That's why it's called super dense coding. And quantum teleportation is something opposite to that, we can say. It's a technique for transferring quantum information from a sender to a receiver some distance away in using a classical channel. For example, I have a quantum information or a qubit. I want to send it to another person, but I don't have a quantum channel to send. I have only a conventional or a classical channel. So what I can do is, you can do some manipulation and give classical data and help him to get the information, quantum information what I have. So that is what is called quantum teleportation. So let's see how it works. So we'll start with superdense coding. So Alice wants to send this classical data to Bob. So what she needs is a help from us. We are Charlie. So we have to create an entangled pair, right? So we will take two qubits which are in 0 state, apply Hadamard gate, apply controlled NOT gate. Now we have two entangled qubits. So whether they are entangled or not, we will see when we go to the simulator. Okay. So now we assume that they are entangled. One entangled qubit you give it to Alice and one to Bob. See, I forgot to mention that when you make an entangled pair and then you can give it to any far distance, they will maintain their property. So that's what was mentioned by Einstein as spooky action at a distance. So even if you take one qubit to Mars, still they have that relationship between them. So that is the speciality of entanglement. Okay, so now Alice has got an entangled qubit with her. So she wants to send 0 1. So this table she will refer to send what data and what gates she has to apply. So to this qubit she will apply in to send 0 1 Z gate. So that she applies and send the qubit to Bob. So now Bob has got two qubits. One directly came from us, Charlie. The other one is some manipulation done by Alice. So with on the two qubits, he applies control NOT and Hadamard gate, and when he makes a measurement, he will get the classical information 0 and 1, like a magic. Okay, we will see whether it will work or not in the simulator. So teleportation, similar way. So we as Charlie will create an entangled pair. One we will give it to Alice and another one will give it to Bob. And Alice has got one more qubit on her hand, and that state of that qubit she wants to give it to Bob. And there is something called no cloning theorem in quantum mechanics, meaning she cannot simply copy it. How? Difficult to understand, just we'll take that because we'll not go into the details of quantum mechanics, right? So she wants to pass the information. At that time in the process she will lose that information what she has got. It will be available only with the Bob. So let us see how it works. So now she has got two qubits. So on that she will do some operation, and then she will make a measurement. And with two qubits she will get two classical bit information. That information she will pass on to Bob through classical channel. So it may be a network cable or Wi-Fi. So with that classical information, she will do an operation on the he will do the operation on the qubit what he has received from us. So what operation he does? Again he will refer the same table. So if he gets 0 1 1, so he will apply Z gate to this, and after once he applies that gate, so this qubit will reach the state of the one what Alice had originally intended to give the information. Again it looks like a magic. Okay, so we will see the magic with our own hand. Okay, come on. So this is IBM quiz kit. You are all familiar. We have seen it many times. Okay, so I'll start from the beginning. So we have two qubits, qubit 0 and 1. Both are in 0 state. So let me see here. So this, you know, it will give a kind of reading. So it is both, I mean, it shows that both are in 0 0 state. So what we have to do? We have to entangle them. So how do you entangle them? We have to apply Hadamard and a controlled NOT gate. So now we have entangled. So you can see here they are in 0 0 and 1 1 state, right? We know that they cannot be separated now. I mean, separated means you can separate them, but you cannot represent them in a tensor product factor form. Okay. All right. So we are giving this qubit to Alice. So Alice, what she does, we will say we have seen 0 1 and 1. Let's say she wants to send the information of 1 1 to Bob. So for that she has to apply from the table a Z gate and a NOT gate. Okay, and that she is giving it to Bob. Now Bob has got two gates and he will be doing some operation. I'm sorry, my mouse is not good. Sorry. Okay, now the information what Bob wanted to give, 1 1, it has come here. Great, it works like a magic. So we have entangled the qubits. Alice did some operation and gave the qubit what she want to Bob, and Bob does some operation with the two qubits, one received from us, one received from Alice, and then he got the information what Alice wanted to send. Suppose Alice wanted to send 1 0 1, she would have applied only Z gate. Suppose she wanted to send 0 0, what she would have done? She would not have done anything. She would have simply passed on the qubit to Bob. That is what is happening here. So like this, you can really do the teleportation also. It's something almost, as I told you, kind of inverse of this. But as I told you today, we haven't really made use of this power of entanglement. For example, I would say, like, if I have 50 qubits on our hand, and we entangle 10 pairs, and even if you pass on those 10 qubit to somebody else, and you do some manipulation, they get reflected on the with the other person. So I mean, I'm sure it will give tremendous advantage in future, and you can be one of the persons to make use of this powerful property of qubit entanglement. Okay, so with this, I think I've come to a conclusion. I think I've already taken time. And references, as usual, Wikipedia gives the ultimate references to explain each and every concept for both superdense coding and quantum teleportation. We have seen the ease with which we are working on the simulator quick is a good tool. And certainly, I mean, IBM documentations are ultimate for any understanding with respect to quantum computation. I simply love them. So you can also see those pages. They also, that they give Jupyter notebook. You can write Python code, make use of their functions to try out all those things instead of playing with the blocks what to like a kid. So as an expert, you can write Python code. And last but not the least, certainly this is like a Bible, quantum computation and quantum information textbook. Please read whenever you get time. You will become a master of quantum computation. So with that, what you can do further, you can experiment with Quick and Quizkit. We have two excellent tools, and of course there are other tools from IBM, from Microsoft and Google, IonQ. I mean, everybody gives. Okay, and then you gain more knowledge by adding, deleting, modifying all those things. You see what happened to the state of qubits, whether you are able to solve any problem, I mean existing problem or a new problem using different gates. So you can keep trying, and I'll continue to learn and come back with more videos on quantum computing. So thanks for watching. Till then, bye bye. Thank you very much.